Something is wrong with April this year, and it is not what the headlines are telling you. Washington, Philadelphia, New York, Boston, all of them simultaneously baking in temperatures that belong in late July. The National Weather Service says records will fall. The ridge driving this sits at the 99th percentile of every April on record. Once or twice a decade phenomenon, they say. Statistically rare, impressive numbers. But here is what nobody is connecting. The atmosphere is not doing this on its own. Something underneath the Pacific Ocean, something enormous, something already moving, is pushing the atmosphere beyond what every forecast model predicted. This heat wave is not the event. It is the announcement of the event. Stay until the end. Because what is coming may make this look like a rehearsal. If this has you thinking, hit like and subscribe to the Skylab so you do not miss where this story goes, because we are nowhere near the end of it. And drop a comment below. I genuinely want to know where in the world you're watching this from, what time it is there, and your honest reaction to this one question. If the atmosphere is already doing this in April, what does August look like? Tell me what you think. Now let's get into it. Now, Part 1. The signal nobody is framing correctly. Something is wrong with the weather this April. Not wrong in the way that makes for a mildly interesting weather segment on the evening news. Wrong in the way that makes atmospheric scientists pull up their data twice, squint at the numbers, and quietly say to each other, this shouldn't be doing this yet. Right now, as you are watching this, the eastern United States is baking. Not a gentle warm spring day. Not shirt sleeves weather that feels nice after a long winter. We are talking about Washington, D.C. pushing toward 90 degrees Fahrenheit. Philadelphia doing the same. New York City pressing against records that have stood for generations. The interior of Boston, a city that was still brushing snow off its sidewalks not long ago, now sitting in air that feels more like July than April. And here is the first thing you need to understand before we go any further. These cities do not do this together. They do not synchronize into record heat in mid-April as a group. That geographic scale from the mid-Atlantic all the way up through southern New England, multiple major population centers all hitting the same extreme at the same time, that is not a local anomaly. That is a signal. And the frustrating thing, the thing that made me want to make this video, is that almost nobody is framing it correctly. The National Weather Service has been remarkably blunt about what is happening. Their offices up and down the East Coast have been issuing statements about widespread records expected to fall. Not might fall, expected to fall. That is the language of forecasters who have looked at the data and are no longer hedging. And what is driving all of this is a ridge of high pressure, a dome of warm, sinking air sitting over the eastern United States at a level that is genuinely difficult to overstate. When meteorologists analyze atmospheric pressure at what they call the 500 millibar level, roughly the middle of the atmosphere, about 18,000 feet up, they look at how high that pressure surface is sitting. Higher means warmer, more compressed air below it. And right now, that height anomaly over the eastern United States is sitting at the 97th to 99th percentile for this time of year. Let that sink in for a moment. Out of every April day in the entire historical record, this atmospheric structure ranks in the top 1 to 3%. We're not talking about a slightly unusual spring afternoon. We're talking about a configuration of the atmosphere that occurs, statistically, once or twice per decade. And yet here we are in the middle of it, and most of the coverage treats it like a quirky warm spell. Move along, nothing to see here. But there is something to see here, and it matters far more than the temperature reading on your phone. Because here is where things get interesting in a way that should genuinely unsettle you. Forecast models, the incredibly sophisticated computer systems that modern meteorology runs on, were already flagging this heatwave as exceptional. Meteorologists at National Weather Service offices looked at those model outputs, which were already showing record warmth, and they adjusted their forecasts upward. They saw the numbers, thought them a bit high, ran their expertise through the data, and still bumped the expected temperatures higher than the raw model suggested. And then the actual temperatures came in and exceeded even those adjusted forecasts. The models got it wrong. The experienced human forecasters who corrected the models got it wrong too. Reality outperformed both of them. The atmosphere showed up hotter than the best prediction we had. Now, when a weather event unfolds exactly as forecast, that is the system working. When a weather event outperforms every layer of human prediction, on top of sophisticated computational modelling, that is a sign something is not fully accounted for. Something in the atmosphere is responding more strongly than our inputs would suggest it should. And that gap between what the physics says should happen and what is actually happening, that gap is the story. Because this is not the peak. This is not the climax of some atmospheric drama that is almost over. What we are watching right now, these record April temperatures breaking across the eastern seaboard, is the opening act. It is a preliminary signal from a system that has not yet fully arrived, and what is coming from beneath the Pacific Ocean to finish what this has started should concern you far more than any single afternoon in the upper 80s. We will get there, but first we need to understand exactly how anomalous this atmospheric structure really is, because the numbers tell a story that the headlines are completely missing. The atmosphere has already started responding. The question nobody is asking loudly enough is, responding to what? Part 2. The pattern is overperforming expectations. Let us go one layer deeper into the atmosphere, because the surface temperature numbers, as dramatic as they are actually not the most alarming part of what is happening right now. Meteorologists do not just watch what the air feels like at ground level. They track temperature profiles through the entire column of air above you, and one of the most telling measurements they use is the temperature at what is called the 925 millibar level, roughly 2,500 feet above the surface, the lowest layer of what we consider the free atmosphere. This measurement tells you something important. It tells you about the air mass itself, not just what the surface is doing in response to sunshine. And right now, over New England, a region that in mid-April should have air mass temperatures at that level, sitting somewhere around 5 to 10 degrees Celsius, the readings are coming in between 15 and 21 degrees Celsius. That is not a small deviation. That is the thermal signature of a summer air mass sitting over a region that has no business hosting summer air in the second week of April. The warmth is not just at the surface because the sun has been heating the ground all day. The warmth extends upward through the lower troposphere, which means the air itself, the raw material of the atmosphere over the region, has been replaced with something that belongs in July, not April. And here is why that distinction matters. On a typical warm spring day, surface temperatures can spike into the 80s because of strong sunshine hitting dry ground, even if the air mass itself is only moderately warm. You get a surface heating effect that flatters the temperature reading. But when the air mass itself is anomalously warm, when the heat extends up through the column, you are dealing with something thermodynamically different. You're dealing with an atmosphere that has been loaded with thermal energy from somewhere else, advected in on a flow pattern that is pulling warm air from regions that should not be releasing this kind of warmth in April. And crucially, this is happening without the amplifying effect of high humidity. Heat index is roughly equivalent to actual temperature right now across much of the affected area. There is no moisture adding phantom degrees to the reading. The number you see is real. That is a pure thermodynamic anomaly, unvarnished by humidity tricks. What makes this even more remarkable is what the National Weather Service has been saying about model performance. Forecast verification, the process of comparing what models predicted with what actually happened, has been showing something that forecasters find genuinely uncomfortable. The forecasts, already adjusted warmer than raw model output suggested, have still been verifying on the warm side. The atmosphere keeps coming in above expectation. There is a term for this kind of situation, forcing mismatch, and it describes what happens when the atmospheric response to a given set of inputs is stronger than the physics of those inputs would normally produce. Something is amplifying the system beyond the expected relationship between cause and effect. Think of it this way. You set your oven to 350 degrees and the thermometer inside reads 420. You have not changed what you put into the oven. The oven itself is outputting more heat than the dial setting would predict. In atmospheric terms, that extra output has to come from somewhere. Energy does not appear from nothing, which means there is an energy source that the models are not fully capturing, a forcing agent whose influence is being underestimated, or perhaps not yet fully incorporated into how we are reading the situation. And the ridge is not behaving like a transient feature either. This is not a system that swept through and is now departing. The ridge has been persistent, slow-moving, maintaining its position and intensity over multiple days. It is sitting over the eastern United States like it has decided to stay a while. That kind of persistence is characteristic of blocked patterns, atmospheric configurations where the normal west to east progression of weather systems stalls out and the same setup repeats day after day. Alongside the heat, fire weather conditions have developed across parts of the region. The same dynamics that are producing the heat are also producing low relative humidity. And when you combine anomalous warmth with dry air and any kind of wind, you create the conditions where a single spark can become something far worse. This is not the primary story today, but it is worth noting that the consequences of this atmospheric pattern extend well beyond the discomfort of a hot afternoon. So we have an unusually deep ridge, performing beyond model expectations, sustained over multiple days, driven by an air mass that has no historical business being over New England in April. The question that should be forming in your mind right now is the same one that forms in the mind of any honest atmospheric scientist staring at these numbers. What is feeding this? Because something is pushing the atmosphere beyond expected limits, and the answer is not sitting in a weather model, it is sitting at the bottom of the Pacific Ocean. But before we go there, we need to zoom out, because this heat wave is not happening in isolation. It is one piece of a planetary scale atmospheric pattern that is simultaneously expressing itself in 5 completely different ways across the North American continent. And when you see all 5 of them together, the picture becomes far more disturbing than any single record temperature. Part 3. 5 extremes, 1 pattern. Here is something that almost never gets reported correctly. When you turn on the news and see coverage of a heat wave in the mid-Atlantic, flooding in the Midwest, fire weather in Texas, snow in the Rockies, and severe storms ripping through the Great Lakes region, all in the same week, the coverage presents these as separate stories, different anchors, different segments, different maps. As if the atmosphere had decided, for some perverse reason, to generate 5 completely unrelated emergencies simultaneously across 5 different parts of the same continent. But here is the thing about the atmosphere. It does not do separate stories. Every one of those events is a different sentence in the same paragraph. They're all expressions of a single planetary scale pattern that is currently running at an intensity that meteorologists find historically unusual for this time of year. What connects all of them is a phenomenon called ridge-trough coupling. Think of the atmosphere as a river. Under normal conditions, that river flows in a relatively even path, meandering modestly as it moves from west to east across the continent. But under certain conditions we are going to talk about in detail, that river starts to develop extreme bends. It carves deep southward plunges, called troughs, alternating with massive northward surges, called ridges. And when those bends become large and slow-moving, they stop being just weather features. They become the organizing principle of an entire continent's atmospheric behavior. Right now, the ridge over the eastern United States, the one driving record April heat from Washington to Boston, is one side of one of those bends. And on the other side of that bend, in the trough embedded over the central part of the continent, you have the opposite extreme. The severe thunderstorm outbreaks tearing through the Midwest and Great Lakes region are happening because warm, moist air from the south is being pulled northward on the eastern flank of that trough and slamming into cooler air draped across the region, exactly the kind of collision that generates violent convection. The flooding in Michigan and Wisconsin is not a coincidence happening alongside the heat wave. It is the same atmospheric wave expressing itself differently because the local ingredients happen to support heavy rainfall instead of heat. Rivers in those regions have been at or near flood stage because repeated rounds of storms, steered by that persistent trough, have been dropping heavy rain on the same areas over and over again. The fire weather in the Texas Panhandle is developing because that same ridge-trough pattern is drawing dry air southwestward into a region where vegetation is already stressed and relative humidity has been falling, and the snow and freeze conditions in the Cascades and Rockies, that is the cold air being wrung out on the western side of the trough, pulled down from Canada into higher elevations, where it produces significant late-season snow even as the East Coast sweats. The physical mechanism underlying all of this is Rossby wave amplification. Rossby waves are enormous undulations in the jet stream, atmospheric waves so large that you need a map of an entire hemisphere to see them properly. They are not storm systems, they are the architecture of the atmosphere at planetary scale. And like waves in any medium, they can amplify. When the conditions are right, when there is sufficient energy available and the right gradients in place, these waves grow taller, their ridges reaching farther north, their troughs plunging farther south. The jet stream starts to look less like a gently meandering river, and more like a series of dramatic switchbacks carved into a canyon wall. And when that happens, The extremes at each bend intensify. The heat dome gets hotter, the cold trough gets deeper, the boundaries between them become more abrupt and more energetic. More severe weather, more flooding, more fire risk, more anomalous warmth, all happening simultaneously because they are all manifestations of the same amplified wave structure. The rarity here is worth emphasizing. We do not typically see all 5 of these categories of extreme weather, major heat, severe storms, flood-producing rainfall, active fire weather, and significant late-season snow occurring simultaneously across the continent in April. Each one individually is unusual for the season. All 5 together, physically linked by the same atmospheric wave, is a pattern that demands explanation. And the explanation leads us directly back to the central question of this entire video. Why is the atmosphere this amplified in mid-April, before the forcing that normally drives such patterns has even officially arrived? Because there is something that sets the stage for these kinds of amplified Rossby wave patterns historically, and it is the same thing that causes the worst of the worst atmospheric extremes in the Northern Hemisphere. It is called an ENSO transition, and here is the problem: we are technically not there yet. Which makes what we are watching right now genuinely mysterious. Part 4. This shouldn't be happening yet. Let us talk about something that should be making more headlines than it is, because it goes to the core of why this heatwave is not just a notable weather event, but a potentially significant atmospheric warning signal. Right now, the official classification of the El Niño Southern Oscillation, ENSO, is neutral. That means the equatorial Pacific Ocean, the great engine of global climate variability, is neither in El Niño nor La Niña territory. The standard metric used to define ENSO status is called the Oceanic Niña Index, or ONI, and for El Niño to be officially declared, that index needs to exceed positive 0.5 degrees Celsius and hold there for 5 consecutive overlapping 3-month periods. We are not there. The current ONI value is sitting well below that threshold. By the official accounting, El Niño has not arrived. The system is neutral. Stand down. Except the atmosphere did not get that memo, because here is the atmospheric pattern we are currently living inside. A highly amplified ridge over the eastern United States sitting at the 97th to 99th percentile, surface temperatures running above every adjusted model forecast, record April warmth from Washington to Boston, 5 simultaneous categories of continental extremes linked by an amplified Rossby wave structure. This pattern, this specific type of atmospheric configuration, is textbook El Niño teleconnection. It is what you would expect to see if a mature El Niño were already in place, driving the kind of sustained atmospheric reorganization that comes from a persistently warm equatorial Pacific pumping extra energy into the global circulation. And yet, by the official metric, El Niño does not exist. What we are witnessing is a temporal mismatch. The atmosphere is behaving like El Niño has already begun, while the official classification system is still saying neutral. And before you conclude that this just means the classification system needs to catch up, consider what that lag actually implies. The ONI is a lagging indicator by design. It is a 3-month running average of sea surface temperatures in a specific region of the equatorial Pacific. That averaging process smooths out variability and ensures that we are not declaring El Niño every time there is a brief warm anomaly in the Pacific. It is deliberately conservative, and that conservatism has real value in scientific communication. But the cost of that conservatism is that it can obscure what is actually happening in real time. And right now, in real time, the data is telling a very different story than the official classification. Look at the ONI trend over the last 6 months. 6 months ago, the index was sitting at negative 0.55 classic La Niña territory. Cold, equatorial Pacific. The atmosphere organized accordingly. Then something changed. The ONI has started warming, rapidly. The ONI has moved from negative 0.55 to negative 0.16 in approximately 6 months. That is a trajectory of nearly 0.4 of a degree of warming in half a year, and the trend has been consistently upward with no sign of reversal. At that rate of progression, the ONI will cross the El Niño threshold not in some distant future scenario, but potentially within weeks. The system is warming fast, and the reason the atmosphere is already responding, the reason we are already seeing El Niño-like patterns before El Niño is officially declared, is that the ocean does not wait for the ONI to catch up before it starts communicating with the atmosphere. The ocean and atmosphere talk to each other in a language that is faster and more direct than any classification system. Warm water, in the right locations, alters the distribution of atmospheric convection, the thunderstorm activity that drives a large-scale circulation. That altered convection modifies where the jet stream wants to go and how amplified it becomes. And those jet stream changes manifest as the exact kind of pattern we are watching unfold across the North American continent right now. The atmosphere is not responding to the ONI number, it is responding to the actual state of the ocean, and the actual state of the ocean is significantly further along than the official index suggests. But here is the part that truly should unsettle you. The warming we can measure at the surface of the Pacific, the warming that the ONI is slowly beginning to capture, is only a fraction of the actual thermal energy that has been accumulating. Because the real story is not happening at the surface of the Pacific, it is happening hundreds of meters below it, in water that no satellite can directly observe, in a layer of ocean that is currently storing an amount of heat that, when it surfaces, will change everything. And we are watching it move. The answer to why the atmosphere is behaving like this was never in the sky. It was always in the ocean. And what is sitting beneath the surface of the Pacific right now is something we need to talk about very carefully. Part 5. The subsurface is the real story. You cannot see what is driving this from the surface. That is the most important sentence in this entire video, and I want you to hold it in your mind as we go through the next several minutes. Because everything we have discussed so far, the record April heat, the amplified Rossby wave pattern, the 5 simultaneous continental extremes, the atmosphere performing beyond every model expectation, all of it is a surface manifestation of something that is happening right now in the dark, cold water hundreds of meters below the surface of the equatorial Pacific Ocean. And if you want to understand why this April heat wave is a warning signal rather than just a weather event, you need to understand what is moving beneath that ocean right now, because it is extraordinary. Copernicus Marine Service has been publishing subsurface Pacific Ocean temperature data, and the numbers are the kind that make oceanographers go quiet for a moment before they start talking. In certain regions of the subsurface equatorial Pacific, not the surface, but the water column extending downward from the surface to depths of around 100 to 300 meters, temperature anomalies are sitting at approximately 5 degrees Celsius above average. 5 degrees. To give you context, a 2-degree anomaly in the equatorial Pacific is enough to force significant reorganization of global atmospheric circulation. 3 degrees produces what we typically call a strong El Niño. 5 degrees in the subsurface water column is the kind of thermal loading that, when it surfaces, rewrites the atmospheric rulebook for the entire planet. And it is moving. That is the critical part. This is not a static pool of anomalously warm water sitting somewhere harmlessly in the depths. It is migrating eastward across the equatorial Pacific, carried by a specific oceanic mechanism called a downwelling Kelvin wave. Kelvin waves are among the most important and least discussed features in the entire climate system. They are not surface waves like what you see at the beach. They are subsurface pressure waves that propagate along the equator, moving from west to east, carrying with them a deepening of the warm water layer. When a downwelling Kelvin wave passes through a region, it pushes the thermocline, the boundary between warm surface water and cold deep water, downward. This effectively buries cold water deeper and raises the temperature of the upper ocean. And when that process happens at sufficient scale, it prepares the ocean surface to warm dramatically once the wave reaches the eastern Pacific, where the warm water can rise to the surface and directly interact with the atmosphere. The mechanism driving these Kelvin waves right now is westerly wind bursts in the western Pacific, brief but powerful reversals of the trade winds that generate the subsurface pressure pulse that becomes the wave. These bursts have been occurring repeatedly over the past several months, each one sending another thermal pulse eastward through the ocean. Think of it as the ocean receiving repeated doses of energy, not one big event, but a series of sustained pushes, each one adding to the eastward migration of that warm subsurface pool. The system is being loaded, methodically, repeatedly, and the heat we are measuring 5 degrees above normal in the subsurface water is not arriving at the surface yet. It is still travelling, still building, and the atmosphere above the eastern United States right now, today, is already reacting to a signal that has not yet fully surfaced. The reason this matters directly to the April heat wave we are living through is not abstract. Warmer ocean temperatures, even subsurface ones, alter the distribution of deep atmospheric convection in the Western Pacific and the tropics. That altered convection changes the Madden-Julian oscillation and the Walker circulation, which in turn modify where the subtropical jet stream sits and how energetic it becomes. Those jet stream changes then propagate downstream, eastward, into the North American circulation pattern. The enhanced ridge over the eastern United States, the amplified Rossby waves, the atmosphere outperforming model expectations, these are the downstream fingerprints of an ocean that has been building towards something for months. The subsurface anomaly is the engine. The April heat wave is exhaust from that engine, and the engine has not even reached full power yet. Part 6. The ONI is lagging reality. Here is a thought experiment that cuts straight to the core of a problem that hides in plain sight whenever people talk about El Niño. It is not that the science is wrong. It is that the way the science is packaged for classification can lag behind the reality it is trying to describe. Imagine you are a doctor trying to determine whether a patient has a fever. You have two tools available to you. The first is a real-time thermometer reading taken right now, in this moment, giving you a direct measurement of the patient's current state. The second is a rolling average of their temperature over the last 3 months smoothed out to remove noise and variability, giving you a stable sense of their recent thermal history. Both tools are useful, both are scientifically valid, but they answer different questions. The real-time measurement tells you what is happening now. The 3-month average tells you what has been happening broadly over time. The Oceanic Niño Index, the ONI, functions much more like that 3-month average than the real-time thermometer. It is deliberately designed to smooth out short-term fluctuations in sea surface temperatures across the Niño 3.4 region of the equatorial Pacific. That smoothing is not a flaw, it is intentional. It helps scientists avoid false alarms and ensures that what is being classified as El Niño or La Niña reflects sustained conditions rather than temporary spikes. But there is a trade-off. By smoothing the data, you introduce a delay. The ONI does not lead the system, it follows it. By the time the ONI officially crosses the threshold into El Niño territory, defined as a sustained anomaly of plus 0.5 degrees Celsius or higher over multiple overlapping 3-month periods, the ocean has usually been warming for weeks or even months. The classification, in a very real sense, is catching up to something that has already been unfolding beneath the surface, and that brings us to where we are right now. 6 months ago, the ONI sat at around negative 0.55 degrees Celsius. That is not just neutral, it is firmly within La Niña territory. The Pacific at that time was characterized by cooler than average surface waters in the central equatorial region, and the atmospheric circulation patterns associated with La Niña were in place. Trade winds were stronger. Warm water was pulled farther west. The system, as a whole, was operating under a cold phase configuration. Then the shift began. The ONI moved from negative 0.55 to roughly negative 0.39, then to negative 0.24, then to negative 0.16. Each update representing a 3-month rolling window, each one stepping upward along a clear warming trajectory. On paper, that still reads as neutral. The official classification has not changed, but the direction is unmistakable. If you extrapolate that trend forward, the index crosses zero, the point where the anomaly becomes positive in the very near term, and from there, reaching the plus 0.5 threshold required for an official El Niño declaration becomes less a question of if and more a question of timing. Weeks, perhaps a couple of months, depending on how quickly the warming continues. But focusing on that threshold misses the deeper point, because while the ONI is still hovering below the line, the leading indicators, the real-time signals of where the system is going, are already far ahead. The most important of those signals sits beneath the surface of the Pacific Ocean. Subsurface temperature anomalies, in some regions, are running as high as 5 degrees Celsius above average. That is not a subtle deviation. That is a massive reservoir of heat stored below the surface, moving eastward along the equator in the form of downwelling Kelvin waves. These waves are not theoretical constructs. They are measurable, trackable pulses of warm water that propagate across the Pacific, deepening the thermocline and pushing heat toward the surface in the central and eastern basin. When they arrive and begin to surface, they often mark the transition from a subsurface-loaded state to a fully realized El Niño at the surface. Right now, that process is underway. The ONI, by design, does not capture this subsurface heat directly. It only measures sea surface temperatures, and even then, only as a smoothed average over time. So while the ocean beneath is already reorganizing itself, the official index is still averaging in older, cooler data from previous months. The result is a number that understates the speed and magnitude of the current transition. If you shift your perspective from 3-month averages to weekly data, the picture sharpens dramatically. Recent sea surface temperature readings in the Niño 3.4 region are running warmer than the ONI suggests, precisely because the most recent weeks have seen accelerated warming. The averaging process dilutes that signal, blending it with earlier, cooler weeks that are no longer representative of the current state. It is the difference between looking at a slow-moving average and watching a system in motion. And when you look at the system in motion, it does not look neutral. It looks like something that is actively transitioning toward El Niño conditions. History offers a useful, if slightly unsettling, comparison. Before the 1997 to 1998 El Niño, the event that remains one of the strongest in the modern record, the Pacific exhibited a similar pattern. Subsurface heat began building and migrating eastward months before the surface temperatures crossed the official thresholds. Scientists who were tracking the deeper ocean signals saw the potential for a major event developing well in advance. But those relying primarily on surface indices like the ONI saw a system that still appeared neutral or only weakly positive. When the atmospheric response finally locked in, it did so rapidly and with intensity that caught many off guard. A similar, though not identical pattern preceded the 2015 to 2016 El Niño. Again, subsurface anomalies provided early warning. Again, the official classification lagged behind the underlying physical reality. The lesson from those events is not that the ONI is flawed. It is that it is incomplete as a real-time diagnostic tool. It tells you what the system has been doing. It does not fully capture what the system is about to do. And right now, the gap between those two perspectives is widening. The ONI trend itself is already signalling rapid change. A shift of roughly 0.4 degrees Celsius over 6 months is not trivial. It indicates a system in transition, moving away from La Niña conditions and towards something warmer. But the subsurface data, the weekly surface trends, and critically the atmospheric behavior we are observing in real time, all suggest that the transition is further along than the index alone would imply. This is where the atmosphere enters the picture in a way that is difficult to ignore, because the atmosphere does not wait for an index to cross a threshold before responding. It reacts to the actual distribution of heat in the ocean. It responds to gradients, to anomalies, to the shifting balance of energy between the ocean and the air above it. And what we are seeing right now over the United States, the record-breaking April heat, the unusually strong ridge of high pressure, the simultaneous extremes across multiple regions, is consistent with an atmosphere that is already responding to a warming Pacific. Not to a fully developed El Niño, but to the precursor state, to the loading phase. It is as if the system has already begun to reorganize itself in anticipation of what is coming, rather than waiting for the official signal. This is why the April heatwave matters beyond its immediate impact. On its own, a stretch of 80s and 90s in April, while unusual, is not unprecedented. But when it occurs in conjunction with the Pacific that is rapidly warming beneath the surface, when it aligns with atmospheric patterns that resemble those typically associated with a mature El Niño, it becomes something else. It becomes evidence. Evidence that the atmosphere is responding to conditions that the official classification has not yet fully acknowledged. Evidence that the system is, in a sense, ahead of schedule. And that raises an important question. If the atmosphere is already producing this level of response while the ONI is still below the El Niño threshold, what happens when the threshold is crossed? What happens when the subsurface heat fully surfaces, when the feedback loops strengthen, when the ocean atmosphere coupling completes? That is not a question with a precise answer, but it is a question that becomes more urgent the more you understand the limitations of the tools we use to define where we are. Because the ONI will eventually confirm what is happening. It will cross into positive territory. It will, if current trends continue, reach the El Niño threshold. And when it does, it will provide a clear official label for the state of the system. But by then, the system itself may have been operating in that state for some time, which means that if you are relying solely on that label to understand what is happening, you're always looking slightly in the rearview mirror. The real story is unfolding in the leading indicators, in the subsurface heat, in the rapid surface warming, and in the atmosphere that is already beginning to behave as if the transition is well underway. And that brings us directly to the next piece of the puzzle. Because if the subsurface tells you where the system is going, and the atmosphere tells you how it is already responding, then the ocean surface, particularly along regions like the California coast, shows you what happens when that hidden heat begins to break through into full expression. Part 7. Surface Confirmation, the California Shock. There is a stretch of ocean along the California coast right now that does not look like April. It does not behave like April. And if you saw it without context, just a map, just a snapshot of the data, you would be forgiven for thinking something had gone wrong in the measurement itself. Because what the latest sea surface temperature anomaly maps are showing in the northeastern Pacific is not just unusual. It is record-breaking in a way that forces you to recalibrate your expectations of what the system is capable of this early in the year. According to NOAA's Coral Reef Watch dataset, which tracks sea surface temperature anomalies globally at high resolution, the waters off the California coast are currently at their warmest ever recorded for the month of April. Not the warmest in recent years, not the warmest since the last major marine heatwave. The warmest in the entire April observational record for that region, and it is not confined to a small, isolated patch hugging a particular section of coastline. This is not a localized quirk. The anomaly extends southward along Baja, California, then stretches outward into the central Pacific, where it connects seamlessly with a much larger band of anomalously warm water that runs across the ocean basin all the way toward the Marshall Islands in the western Pacific. What you're looking at is not a hotspot. It is a system, a continuous basin-scale structure of elevated ocean temperatures that happens to be expressing some of its most extreme values right along the Pacific coast of North America. It is as if the ocean itself is drawing a line from one side of the Pacific to the other and saying, this is not regional variability. This is a coordinated shift. To understand how extreme that shift is, you have to look at how marine heat waves are classified. The system used by NOAA and other research groups categorizes marine heat waves into 5 levels. Category 1 represents moderate conditions, above normal, but within a range that ecosystems can sometimes tolerate. Category 2 and 3 escalate in severity. Category 4 is considered extreme, already pushing beyond what most marine systems are adapted to handle. And then there is Category 5. Category 5 is not just very extreme, it represents conditions that exceed the historical range for that location and time of year by such a margin that, statistically, they fall outside what the climatological record would consider normal variability. In other words, you're no longer just dealing with an unusually warm ocean, you're dealing with a state that, based on past data, should not be occurring. Right now, off the coast of Baja, California, that is exactly where the system is operating. Category 5. That means the sea surface temperatures there are not just above average, they are above the previous extremes, surpassing the highest values that have been recorded for April in that region. It is the kind of signal that forces scientists to double-check instruments, cross-reference with buoy data, and confirm that what they are seeing is real. And it is. Because this is not a measurement artifact, it is being observed across multiple datasets, from satellites to in situ buoys, all telling the same story. The northeastern Pacific is running extraordinarily warm, in a way that aligns with a broader pattern we have been tracking across the entire basin. And once you understand that, the next step is to connect it back to what is happening beneath the surface. Because this surface anomaly did not appear out of nowhere. The Pacific over the past several months has been accumulating heat below the surface in the form of those 5-degree above average subsurface anomalies we discussed earlier. That heat has been moving eastward along the equator, carried by downwelling Kelvin waves, gradually approaching the eastern boundary of the ocean basin. When that heat reaches the coast of the Americas, something important happens. The ocean, quite literally, runs out of room. There is no more eastward to go, and so the energy that has been stored below the surface begins to move upward. It surfaces. Under normal conditions, the California and Baja California coastlines are dominated by upwelling. Winds blowing along the coast drive surface waters away, allowing colder, nutrient-rich water from deeper layers to rise up and replace them. This process is what supports the region's rich marine ecosystems. It is why those waters are typically cooler, even when the open ocean farther west is warmer. But that process depends on one key assumption, that the water being pulled up from below is cold. Right now, that assumption is breaking. Because the water beneath the surface is no longer cold, It is anomalously warm. When upwelling occurs, it is not bringing cool water to the surface. It is bringing up water that has been sitting inside that subsurface heat reservoir. So instead of cooling the surface, the upwelling is reinforcing the warmth. It is like turning on a faucet that used to deliver cold water and finding that the entire system behind it has been heated. No matter how much you run it, it does not cool down. The source itself has changed. This is why the marine heatwave off Baja is not a separate story from the subsurface anomalies. It is the same story, just at a different stage. The subsurface signal was the buildup, this is the release. The first visible face of a thermal event that has been developing quietly for months, now breaking through to the surface in a way that can interact directly with the atmosphere above. And that interaction is where this becomes directly relevant to everything happening over land. Because warm ocean surfaces do not just sit there passively, they exchange energy with the atmosphere. They add heat, they add moisture, they alter pressure patterns, they influence the development and persistence of atmospheric ridges and troughs. A Category 5 marine heatwave is not just a number on a chart, it is a massive reservoir of thermal energy sitting at the boundary between ocean and air feeding into the system. Think about the scale of that for a moment. This is not a small contained feature. It stretches along hundreds of miles of coastline and connects to a basin-wide anomaly that spans thousands of miles across the Pacific. The amount of energy involved is enormous, and it is sitting adjacent to a continent that is already experiencing an atmospheric pattern operating at the extreme edge of its historical range. The ridge over the eastern United States, sitting at the 97th to 99th percentile, is already drawing in and redistributing heat. The jet stream is already amplified. The system is already producing multiple simultaneous extremes. Now add to that a coastal ocean that is feeding additional heat and moisture into the atmosphere, not in isolation, but as part of the same interconnected system. This is where proximity starts to matter in a very real way, because the closer that heat is to land, the more directly it can influence atmospheric processes that affect weather patterns over the continent. And it is not just the immediate effect, it is the feedback. Warm ocean surfaces increase evaporation. More moisture enters the atmosphere. That moisture can enhance latent heat release in storms and circulation systems, effectively adding another layer of energy to processes that are already being driven by large-scale dynamics. It is a compounding effect. You have a subsurface reservoir feeding the surface feeding the atmosphere responding in ways that feed back into the larger circulation pattern, and all of it is happening on top of a global ocean baseline that, as we discussed earlier, is already at a record high. This is not a linear system where one cause produces one effect. It is a network of interactions, each one amplifying the others, and that is why the California anomaly matters so much in the context of the April heatwave, because it is not just a regional curiosity, it is a confirmation, a visible, measurable confirmation that the Pacific is not only warming beneath the surface, but has begun to express that warmth at the surface in a way that is consistent with the development of a larger scale event. It tells you that the system is not just loading energy, it is starting to release it. And when you look at the structure of that release, the fact that it connects from the California coast all the way across to the Western Pacific, you start to see something that resembles patterns from the past. Not perfectly, not identically, but recognizably. There have been moments in the historical record where basin-wide warming patterns preceded major El Niño events, where the Pacific began to act as a unified system rather than a collection of independent regions, where anomalies aligned across large distances, reinforcing each other. Those moments are rare, and when they occur, they tend to be associated with some of the most significant atmospheric disruptions on record. But here is the part that makes the current situation different. Those past events did not begin from a baseline as warm as the one we have today. They did not start with a global ocean that had already set a record for its highest average temperature in any month. They did not combine a Category 5 marine heatwave along the California coast in April with a subsurface anomaly of this magnitude and an atmosphere that is already responding ahead of schedule. This is why the historical analogues are useful, but incomplete. They give you a sense of what the system can do, but they do not fully capture what the system might do when those same processes operate on top of a higher baseline and with more energy available. And that is where the discomfort comes in, because when you try to map the current state onto the past, The fit is not perfect. The pieces are familiar, but the configuration is new, which means that the outcomes may not follow the patterns we expect. The California coast in this moment is not just an anomaly, it is a signal that the ocean has entered a state that is capable of producing conditions beyond what we have historically observed for this time of year. And because that ocean is the primary driver of the atmospheric system we are watching unfold, it forces a shift in how you interpret everything else. The April heat wave is no longer just a standalone event, it becomes part of a larger sequence. The ridge, the extremes, the anomalies, they are all interacting with a Pacific that is already showing its hand. And what it is showing is not subtle. It is telling you that the system has more energy than it should at this stage, that it is already expressing that energy in multiple ways, and that the processes responsible for what we are seeing now are not finished, they are just getting started. Part 8. The blob is back, but different. Between 2013 and 2016, a mass of anomalously warm water appeared in the northeastern Pacific Ocean. Scientists called it the blob, which sounds almost whimsical until you understand what it actually did. The blob disrupted the California current, the cold upwelling system that has governed the northeastern Pacific for as long as humans have been measuring it. It eliminated the cold water barrier that normally keeps tropical marine species confined to warmer latitudes, allowing species from hundreds of miles south to appear off the Oregon and Washington coasts. It contributed to the worst California drought in recorded history. It collapsed the Pacific sardine fishery. It generated toxic algal blooms that stretched from Alaska to California, producing shellfish closures along thousands of miles of coastline. And it raised sea surface temperature anomalies in the northeastern Pacific to levels that had not been seen in the modern observational record at the time. The anomalies we are currently measuring off California are comparable in magnitude to what the blob produced at its peak. But here is the critical difference between then and now. The difference that makes the current situation potentially more consequential. The blob occurred during a period when the equatorial Pacific was transitioning toward what eventually became the 2015-16 El Niño, but the blob itself was not El Niño. It was a separate northeast Pacific anomaly that happened to coincide with and compound the equatorial warming. The two signals ran together, but they had different origins and different primary mechanisms. What is happening right now is structurally different, because the northeast Pacific marine heat wave is not running alongside an equatorial Pacific anomaly. It appears to be connected to it. The basin-wide warming pattern that NOAA is measuring, the one that stretches from the Marshall Islands in the west all the way to California in the east, suggests a coherent, connected thermal anomaly rather than two separate events happening to overlap in time. This is not the blob plus developing El Niño. This may be a single, basin-scale thermal event of a kind that has limited historical precedent. That distinction matters because of a concept called nonlinear amplification. When two separate extreme events overlap in time and space, they can produce effects that are larger than the sum of their parts. The atmosphere does not respond to two distinct forcing signals by computing them separately and adding the results. It responds to their combination, and that combination can unlock feedbacks and interactions that neither signal would have generated on its own. A massive northeast Pacific marine heat wave coinciding with a developing equatorial El Niño is not El Niño plus a regional marine heat wave in terms of its atmospheric impact. It is a compound event whose total influence on atmospheric circulation could exceed what either component would produce in isolation. And we do not have a robust set of historical examples of that compound event at this scale to tell us exactly what to expect. The uncertainty here is genuine. What we can say is this: the current state of the Pacific Ocean, from the surface down to hundreds of meters, represents an accumulation of thermal energy that is historically unusual even before El Niño officially arrives. The subsurface anomalies are larger than what preceded major past events. The surface warming is already reaching Category 5 marine heat wave intensity in some regions. The basin-scale coherence of the warming pattern suggests a system that is more connected and more energetically loaded than typical El Niño precursor states. And the atmosphere is already responding, not to a fully developed El Niño, but to this precursor state. If the precursor is already producing record April heat waves at the 97th to 99th percentile of atmospheric intensity, what does the fully developed event look like? That question does not have a comfortable answer. But to even begin to approach it, We need to understand the specific mechanism by which ocean heat becomes atmospheric chaos. Because the bridge between a warm Pacific and a heat wave in Boston is not obvious, and once you understand how it works, the scale of what may be coming becomes considerably harder to dismiss. Part 9. Rossby wave amplification on steroids. Picture the jet stream as a river of air flowing around the northern hemisphere at roughly 30,000 feet altitude, moving from west to east, carrying weather systems with it. Under normal conditions, that river meanders. It dips south here, rises north there, but the deviations are modest and the overall flow is relatively efficient, moving air and energy around the hemisphere at a reasonable pace. Now imagine heating up the water on one side of that river, warming the ocean below its southern flank, adding energy to the tropical and subtropical atmosphere in ways that change the temperature contrast between tropical and polar air. When the temperature difference between the tropics and the poles decreases, which happens when the tropics warm faster than the poles, or when the poles also warm significantly as they have been, the jet stream weakens. And a weakened jet stream is a jet stream that meanders more. Its bends get bigger, its ridges push further north, its troughs plunge further south, and the whole river starts to look less like an efficient highway and more like a river that is trying to carve canyon walls through solid rock. This is Rossby wave amplification, and it is the atmospheric mechanism that turns a warm Pacific Ocean into a continental catastrophe. The Rossby waves we are currently watching over North America are not subtle. The ridge over the eastern United States, sitting at the 97th to 99th percentile of height anomaly for this time of year, represents a northward bulge of the jet stream that is statistically unprecedented in the April record. The trough sitting over the central continent, driving severe weather and flooding, is the corresponding southward plunge on the other side of the bend. The amplitude of this wave, the distance between the peak of the ridge and the bottom of the trough, is operating at a level that produces all 5 categories of simultaneous extreme weather that we catalogued earlier. This is not the jet stream doing something modest. This is the jet stream doing something extreme in a way that has a direct physical cause and a direct physical connection to the thermal state of the Pacific Ocean. The mechanism linking Pacific Ocean warmth to Rossby wave amplification runs through the tropical convection that warm ocean temperatures generate. When ocean surface temperatures in key regions of the tropical Pacific rise above the threshold for deep convection, roughly 28 degrees Celsius, thunderstorm activity intensifies and organizes into large-scale convective systems. Those systems heat the upper troposphere through what is called convective heating, releasing latent heat energy as moisture condenses at altitude. That upper tropospheric heating creates pressure anomalies that propagate poleward through the atmosphere as Rossby waves, literally, the energy from tropical thunderstorms generated by a warm Pacific, travels north and northwest through the atmosphere and reaches the jet stream, where it reshapes the wave pattern. The warmer the Pacific, the more intense the convection, the stronger the Rossby wave forcing, and the more amplified the jet stream pattern becomes. This is not theoretical. This is the documented, well-understood physical pathway that connects ocean temperature to weather extremes thousands of miles away. And here is the current state of that pathway. It is more loaded than it normally is in April, because the ocean temperatures generating the tropical convection are already running at levels that typically correspond to a fully developed El Niño rather than a neutral to transitioning state. The subsurface warming we discussed, the surface anomalies approaching Category 5 marine heatwave intensity, the basin-wide coherence of the Pacific thermal anomaly, all of these are combining to generate a Rossby wave forcing that the atmosphere is responding to with the full amplification we see in the current pattern. And this is happening before the system has officially arrived. The wave is already running at maximum amplitude. The ridge is already at the 99th percentile. The heat is already breaking April records. What happens to the amplitude of this wave when the subsurface heat finishes surfacing? What happens to the ridge when the full equatorial Pacific warming reaches the surface and begins generating the kind of sustained convective forcing that a mature super El Niño can produce? We do not know exactly, but the trajectory of the physics points in one direction. The atmosphere is showing us the answer before the question has been fully asked. There is a scientific debate worth mentioning briefly. Whether the increasing frequency and amplitude of these Rossby wave amplification events in recent decades is directly attributable to climate change, specifically to Arctic amplification, The phenomenon where the Arctic is warming roughly 4 times faster than the global average, reducing the temperature contrast that keeps the jet stream strong, is still an area of active research and genuine scientific disagreement. Some studies show a clear statistical link between Arctic amplification and increased jet stream meandering. Others find the signal less clear or potentially masked by natural variability. The honest answer is that the science is not fully settled. But what is not debated is the physics of the current event. The atmosphere over North America right now is running a wave pattern of extraordinary amplitude. The Pacific Ocean beneath it is anomalously warm at depths and extents that dwarf typical April baselines. The energy source is real, the atmospheric response is real, and the implications of both together are what we need to think about when we ask what comes next. Part 10. The preconditioning effect. There is a concept in atmospheric science that rarely makes it into mainstream weather coverage, but which I think is the single most important idea for understanding why this April heatwave is more significant than it appears. That concept is preconditioning, and it means exactly what it sounds like: a system being set up, primed, loaded with energy and structural bias before the main event arrives. Think of it as the difference between trying to knock over a wall that has never been touched and trying to knock over a wall that has already been undermined at the foundation. The same force produces completely different outcomes depending on the state of the target. The wall that has been preconditioned, its structural integrity already compromised, falls with far less force than the one that starts from a neutral baseline. The current state of the atmosphere over North America and the Pacific Ocean underneath it is a preconditioned system. And the preconditioning has been running for months. Here is how it works in specific physical terms. The subsurface Pacific warm water we have been discussing, the pool of 5 degrees above average water migrating eastward through the ocean, does not sit inertly in the deep Pacific waiting for the moment it surfaces to begin influencing anything. Even while it is still subsurface, its presence alters the sea surface temperature pattern through processes of heat exchange, changes the depth of the thermocline, and suppresses the upwelling of cold water that would otherwise cool the surface. This means the surface Pacific has been warming more consistently over recent months than it would have in the absence of the subsurface loading. And that surface warming, even modest by comparison to what is coming, has been altering the atmospheric circulation above it, changing where convection occurs, modifying the Walker circulation that connects the tropical Pacific to global atmospheric patterns and adjusting the shape and intensity of the subtropical jet stream. That adjusted jet stream has been communicating its altered structure downstream to the North American continent over a period of weeks to months. Each day of circulation in that jet stream pattern is another day of preconditioning for the downstream atmosphere. The ridge that is now sitting at the 99th percentile of April, height anomalies did not appear overnight from nothing. It built into its current extreme configuration through a gradual process of atmospheric conditioning driven by persistent upstream forcing from an ocean that has been loaded for months. The models that underestimated the intensity of the current heat wave did so partly because they were not fully capturing the extent to which the background state of the atmospheric circulation had been preconditioned by months of subtly altered Pacific forcing. The models see the ingredients for warmth. They do not fully account for how much easier it is to build an extreme ridge when the atmospheric foundation has already been shifted toward that configuration. Early season anomalies of this type, atmospheric extremes appearing significantly earlier in the season than historical patterns would predict, have become more common in recent years. Whether this is noise or signal is a legitimate scientific question, but the current event is not subtle enough to dismiss as noise. A 99th percentile April ridge is not a minor early season anomaly. It is an extreme event, and its extremity relative to historical April baselines suggests something about the state of the background atmosphere that goes beyond natural variability. The threshold for producing an event this extreme in April appears to be lower than it has historically been. The system needs less forcing to produce more response. That is precisely what preconditioning means at the atmospheric scale, and it suggests that the traditional seasonal timing of extreme weather, the assumption that July extremes belong in July and not April, may be less reliable than it once was. The concept of threshold crossing is relevant here. Complex systems, and the climate system is among the most complex on Earth, often behave in ways that are roughly linear within a range of conditions but exhibit abrupt changes in behavior when key thresholds are crossed. We do not know with certainty where all the relevant thresholds are in the climate system, but we know they exist. And when a system is being progressively preconditioned, when the background state is being pushed closer to a threshold over months of gradual loading, the trigger for a threshold crossing can be surprisingly small. A relatively modest additional forcing on top of months of preconditioning can produce a disproportionately large response. The atmosphere is not responding proportionally to its immediate forcing right now. It is responding to the sum of all the preconditioning plus the immediate forcing, and the sum is producing a heat wave that outperforms every model and every adjusted forecast. If this is the atmosphere on preconditioning alone, what does it do when the main event fully arrives? That question is going to frame everything in the final act of this video. But before we get there, we need to take a brief but important detour into the Western Pacific, because while the US East Coast has been baking, the Pacific has quietly produced another piece of evidence that the ocean is already operating well beyond seasonal norms, and that evidence came in the form of a Category 5 typhoon forming at a time of year when it absolutely should not have. Part 11. The Sinlaku Warning Shot. Super Typhoon Sinlaku formed in the Western Pacific in April of 2026, with maximum sustained winds reaching Category 5 intensity on the Saffir-Simpson scale. April, Category 5. This is not typical. The Western Pacific tropical cyclone season does have storms in April. The basin is active year-round, but Category 5 storms in April are rare precisely because the ocean temperatures needed to support that kind of rapid intensification are not normally present this early. Tropical cyclones require ocean surface temperatures of approximately 28 degrees Celsius, or warmer, to maintain deep convection and sustain themselves against the entrainment of dry air and environmental wind shear that tends to limit storm intensity in the lower energy early season atmosphere. Sinlaku formed and intensified rapidly in waters running at 28 to 29 degrees Celsius across a broad stretch of the Western Pacific, temperatures that should belong to July or August in that basin, not April. The ocean heat content across the storm's path, the measure of thermal energy available to the storm not just at the surface, but through the warm water layer beneath, was comparable to what you find at peak season. The storm did not know it was April, the ocean did not tell it. This connects directly back to the central story. Super Typhoon Sinlaku is not a distraction from the April heatwave discussion. It is a data point from a different location that confirms the same underlying signal. The Pacific Ocean is running warm enough in April 2026 to generate peak season, equivalent tropical cyclone intensity in the Western Basin, record April marine heatwave conditions in the northeastern basin, and Category 5 marine heatwave temperatures off Baja, California. The thermal anomaly is not regional. It is not confined to the subsurface. It is expressing itself simultaneously in multiple locations across the entire Pacific system, and in each location it is producing an extreme that belongs in a different month. Sinlaku is the Western Pacific's version of the same story the Eastern US heatwave is telling. The ocean is already operating at a level that the atmosphere is responding to with seasonal extremes that are months ahead of schedule. Part 12. The global ocean baseline has shifted. There is a number that deserves far more attention than it's getting right now, and it doesn't come from a forecast model or a speculative projection. It comes from direct observation. In March 2026, the global ocean set a new sea surface temperature record. Not a record for March, not a seasonal outlier, a record for any month in the entire observational history of global sea surface temperatures. That means, averaged across the entire planet, the ocean was warmer in March 2026 than it has ever been at any point in the modern record. And at first glance, that might sound like just another data point in a long chain of warming signals, but it is not just another data point. It fundamentally changes the context in which every current and upcoming weather event is unfolding. What makes this moment different is not just the anomaly, the departure from average conditions, but the absolute baseline itself. The floor of the system has risen, and that distinction is easy to overlook because most discussions about climate and weather focus on anomalies, how far above or below normal something is. But anomalies only tell you part of the story. They tell you how unusual something is relative to a past average, not how extreme it is in absolute terms, and when the baseline shifts upward, the meaning of every anomaly changes with it. A useful way to think about this is to imagine a swimming pool. The water level represents the global ocean temperature baseline. Waves in that pool represent weather events, climate variability, El Niño cycles, marine heat waves, everything that causes the system to fluctuate. Normally those waves rise and fall within a certain range, sometimes reaching high peaks, sometimes dropping lower, depending on how much energy is in the system. But now imagine that you start filling the pool with more water. The baseline level rises, the floor is no longer where it used to be. Now take the exact same wave, same energy, same structure, nothing about it has changed, and let it move through this now fuller pool. That wave will reach a higher absolute level than it would have before, not because the wave itself is stronger, but because the entire system it exists within has been lifted. The pool is fuller. Every wave, even identical ones, now goes higher. This is exactly what is happening with the global ocean right now. The baseline temperature, the pool level of the climate system, is at an all-time high. And that means every anomaly, every fluctuation, every atmospheric response is now starting from a higher floor. When you hear about a marine heat wave, or a strong ridge of high pressure, or an unusually warm air mass, you're not just looking at the anomaly itself. You're looking at that anomaly stacked on top of a record-breaking baseline. This is where the current situation becomes far more significant than a single heatwave headline might suggest. The Category 5 marine heatwave off Baja, California is not just extreme because of the anomaly alone. It is extreme because that anomaly is occurring on top of the warmest global ocean baseline ever recorded. The waters were already elevated before the anomaly even began. So when the anomaly developed, it pushed temperatures into territory that may not have been reachable in previous decades, even under similar conditions. The same logic applies to the record April heatwave unfolding across the eastern United States. The ridge of high pressure driving temperatures into the upper 80s and low 90s is, by itself, already unusual, sitting in the 97th to 99th percentile for this time of year. But that ridge is not operating in a vacuum. It is operating in an atmosphere that is coupled to an ocean system currently at a record warm baseline. That matters because the ocean is the primary energy source for the atmosphere. Warmer oceans transfer more heat and moisture into the air, increasing the amount of energy available to drive atmospheric patterns. So when that already rare ridge forms over the eastern United States, it is doing so in an environment where the background energy level is elevated. The result is that the atmospheric response, the actual surface temperatures we experience, can exceed what historical analogues would suggest. It is not just that the ridge is strong, it is that the ridge is being fed by a system that is already running hotter than anything we have observed before. This combination, an elevated baseline plus an extreme anomaly, is what creates genuinely unprecedented conditions. Not unprecedented in the sense that no individual component has ever existed before, but unprecedented in the sense that these components are now stacking on top of each other in ways that push the system beyond previously observed limits. It is the difference between a strong event and an event that breaks records across multiple regions simultaneously. And this compounding effect is not something reserved for the future. It is happening right now in real time, contributing directly to what we are seeing in April 2026. The heat wave is not just early, it is not just strong, it is amplified by the fact that the entire system beneath it has shifted upward. What makes this even more consequential is what comes next, because the Pacific Ocean is not just warm, it is actively transitioning. Beneath the surface, large pools of anomalously warm water are moving eastward, a classic precursor signal of El Niño development. If those subsurface anomalies continue to rise and spread across the surface, they will introduce an additional layer of warming on top of an already elevated baseline. To understand why this matters, it helps to look at history. The 1997 to 1998 El Niño remains one of the most powerful on record, producing widespread atmospheric disruption across the globe. The 2015 to 2016 El Niño was similarly strong, driving extreme weather patterns in multiple regions. But both of those events occurred on top of global ocean baselines that were lower than what we are seeing today. The starting point was different. The current system, if it evolves into a comparable or stronger El Niño, will not be starting from the same conditions. It will be building on top of a baseline that is already at record levels. That does not mean we can simply add a degree here or there and predict exact outcomes. Climate systems are non-linear, they do not scale in simple, predictable ways. but what it does mean is that the atmosphere will have access to more energy than it did during those previous events. More energy in the system increases the potential for extremes. It narrows the gap between what we consider severe and what becomes unprecedented. Events that might have been rare but manageable in the past can cross thresholds into territory that lacks clear historical precedent. And that is where uncertainty begins to grow, not because we lack data, but because the system itself is entering configurations that have not been fully observed before. This brings us to a critical point about modelling and prediction. Climate and weather models are built using historical data, physical laws, and statistical relationships. They are powerful tools, and they have improved dramatically over time, but they are still constrained by the range of conditions they have been trained on. When the system begins to operate outside of those historical ranges, when baselines shift, when multiple extremes overlap, when anomalies stack in new ways, the models can begin to struggle. We are already seeing hints of that in the current event. Forecast models for this April heatwave were adjusted upward as new data came in, yet in many cases they still underestimated the actual temperatures observed. That gap between expectation and reality is not necessarily a failure of the models. It is a signal. It suggests that the system may be responding more strongly than anticipated to the underlying conditions. And those underlying conditions are not static. The Pacific is still evolving. The subsurface heat has not fully surfaced. The El Niño signal has not officially emerged. In other words, the system is still in transition. The forcing factors that are driving this early season heatwave are not fully developed yet. That is where the real uncertainty lies. If the atmosphere is already producing record-breaking conditions in response to a partially developed signal, what happens when that signal fully materializes? What happens when the additional heat from a mature El Niño is layered on top of a global ocean that is already at a record baseline? There is no simple answer to that question, and that is precisely the point. We may be entering a regime where historical analogues, our primary reference points for understanding future behavior, become less reliable. Not because the physics has changed, but because the boundary conditions have. The system we are observing today is not identical to the system that produced past extremes. It is operating with more energy, higher baselines, and potentially stronger feedbacks. That does not guarantee that every upcoming event will be more extreme, but it does increase the probability that when extreme conditions do develop, they will have the potential to exceed past limits, and it reinforces the idea that what we are seeing right now, the record April heat, the marine heat wave, the early atmospheric response, is not an isolated anomaly. It is part of a larger pattern, a pattern in which the floor is rising, the waves are building, and the timing is shifting. A pattern in which the system begins to respond before the main signal has even fully arrived. And if that pattern continues, then the events of April 2026 may not be remembered as the peak of anything. They may be remembered as the moment the system started showing its hand early. Part 13. If this is the beginning. Let's slow this down and get very precise about where we actually are in the timeline, because this is where most of the misunderstanding comes from. Right now, as of mid-April 2026, the equatorial Pacific Ocean has not yet crossed the official threshold required to declare an El Niño event. The Oceanic Niño Index, the ONI, is still below the plus 0.5 degrees Celsius benchmark that defines El Niño conditions. On paper, in the datasets, in the official classification system, we are still in neutral territory. If you were to look only at that number and nothing else, you would conclude that the system has not fully transitioned. But that conclusion would be incomplete. Because beneath the surface, literally beneath the surface, the system is already in motion. Large volumes of anomalously warm water, in some places approaching 5 degrees Celsius above average, are moving eastward along the equatorial Pacific. These are not surface anomalies yet. They are subsurface thermal reservoirs, carried by downwelling Kelvin waves, driven by westerly wind bursts that have been occurring over the past several weeks. These waves act like underwater conveyor belts, transporting heat from the western and central Pacific toward the eastern basin, where it can eventually rise and interact directly with the atmosphere. That process is still ongoing. It has not finished. The heat has not fully surfaced. The coupling between the ocean and the atmosphere, the phase where surface temperatures reshape global circulation patterns, is not complete. What we are seeing right now is the loading phase, the buildup, the precondition. And yet, despite the system not having fully transitioned, despite the fact that the official signal has not yet been declared, the atmosphere is already responding. The Category 5 marine heatwave off Baja, California, is not the endpoint of this process. It is the leading edge. It is where the subsurface heat is beginning to break through. And at the same time, across the continental United States, the atmosphere is producing a pattern that, by any statistical measure, is extreme for this time of year. A 99th percentile ridge of high pressure, driving temperatures into the 80s and 90s from Washington, D.C. to Boston in mid-April, while simultaneously contributing to a cascade of other extremes across the country. This is the key point. What we are observing is not the mature state of the system. It is the atmospheric response to a precursor state, to the loading, not the discharge. And once you understand that distinction, a very serious question naturally follows. If the precursor alone, the incomplete, still evolving setup, is capable of producing a 99th percentile atmospheric pattern that outperforms model forecasts and breaks records across multiple major cities, then what does the fully developed system produce? What happens when the heat that is currently subsurface fully surfaces? What happens when the feedback loops that define El Niño lock into place? The honest answer is that we do not know with precision, and that uncertainty is not a weakness in the science. It is a reflection of the complexity of the system we are dealing with. Climate and weather are nonlinear systems, meaning that their responses are not always proportional to their inputs. Small differences in initial conditions can lead to large differences in outcomes. When you add in the fact that the current system is operating on top of a record-high global ocean temperature baseline, you're dealing with a configuration that does not have a perfect historical match. What scientists can do is define a range of plausible outcomes. On the lower end of that range, the system evolves into a moderate or even strong El Niño, but the atmospheric response remains within the bounds of what we have seen before. Summers run hotter than average, severe weather becomes more active, rainfall patterns shift in familiar ways. It is disruptive, but it is not unprecedented in a way that fundamentally rewrites expectations. But there is also an upper end of the range. In that scenario, the subsurface heat fully surfaces, the coupling between the ocean and atmosphere strengthens rapidly, and the resulting feedback loop drives large-scale circulation changes that push the jet stream into configurations that do not closely resemble anything in the modern observational record. In that kind of scenario, you're not just dealing with isolated extremes, you're dealing with persistent pattern shifts, extended periods of heat in regions not adapted to it, prolonged disruptions to rainfall patterns that agriculture depends on, and atmospheric blocking setups that can lock those conditions in place for weeks or even months. Between those two outcomes lies a spectrum, a probability distribution that scientists are actively trying to narrow, and one of the most important clues about where we might fall within that distribution comes from the behavior of the models themselves. Right now, different forecasting approaches, statistical models, dynamical climate models, hybrid systems, are producing a relatively wide spread of outcomes for the coming months. That spread is not random, it is a signal. When models converge tightly on a forecast, it usually means the system is well understood and the range of possible responses is relatively narrow. But when models diverge, when they produce a wide spread of possibilities, it typically means the system is in a sensitive state. A state where small changes in how the forcing evolves can produce significantly different outcomes. That is where we are now. This is a widespread moment. And there is another layer to that. The direction of recent surprises matters. Over the past several weeks, the atmospheric response has not just matched expectations, it has exceeded them. Forecasts have been adjusted upward, and reality has still come in hotter, stronger, more amplified than predicted. That pattern of underestimation suggests that the risk may not be evenly distributed across the range of possible outcomes. It may be skewed toward the stronger end. To understand why, you have to look at how El Niño actually works, not just as a temperature anomaly, but as a coupled system. The defining feature of a fully developed El Niño is not simply warm water in the Pacific. It is the feedback loop that forms between the ocean and the atmosphere once that warm water becomes persistent and widespread at the surface. Under normal conditions, the tropical Pacific is dominated by the Walker circulation, an east-to-west atmospheric circulation pattern. Warm water pools in the western Pacific near Indonesia, where it fuels convection and rising air. That air moves eastward at high altitudes, sinks over the cooler eastern Pacific, and returns westward at the surface as trade winds. Those trade winds in turn push warm surface water back toward the west, reinforcing the system. El Niño disrupts this balance. As warm water begins to spread eastward, the temperature gradient across the Pacific weakens. Convection shifts eastward, the trade winds weaken, and as those winds weaken, they allow even more warm water to move east and surface. This creates a positive feedback loop. More warm water leads to weaker winds, which leads to more warm water, which further weakens the winds. The strength and speed of this feedback loop are what determine how powerful an El Niño becomes, and right now, the conditions in the Pacific are unusually favourable for that loop to activate. The subsurface heat reservoir is already large, the Kelvin waves are already transporting that heat eastward. The background ocean is already warmer than at any point in the observational record. All of these factors increase the likelihood that, once the coupling process begins in earnest, it could proceed rapidly and with significant strength. That is why this moment matters so much. We are not just observing a system in motion, we are observing a system approaching a potential inflection point, a threshold beyond which the dynamics of the system change qualitatively, not just quantitatively. Before the threshold, the system responds in one way. After the threshold, it can reorganize entirely. The April heat wave, in this context, is not the main event. It is the signal that the system is already sensitive enough to produce extreme responses ahead of schedule. It is evidence that the atmosphere is already feeling the influence of a Pacific Ocean that has not yet fully expressed its energy at the surface, and that leads to a final, uncomfortable realization. If the atmosphere is already capable of producing record-breaking patterns in response to a partially developed signal, then the full expression of that signal, when it arrives, may not simply scale up what we are seeing now. It may push the system into behavior that we do not yet fully understand. This is not about predicting a specific outcome. It is about recognizing the structure of the moment we are in. The system is loaded. The energy is there. The coupling process is underway but incomplete. The atmospheric response has already begun, and the range of possible futures remains wide. We are, in other words, watching a system approach the point where its behavior could change. And the most important thing to understand about that moment is this: the April heat wave is not the story. It is the announcement that the story is about to begin. Part 14. Super El Niño Scenario. The term Super El Niño gets used a lot in headlines and online discussions, but it has a very specific scientific meaning, an understanding that meaning is critical if you want to grasp what is actually at stake right now. This is not just a dramatic label for a particularly strong El Niño. It refers to a very narrow category of events that sit at the extreme upper edge of what the climate system has produced in the modern observational record. To understand where that threshold sits, you have to look at how El Niño events are formally classified. The benchmark region is the Niño 3.4 region in the central equatorial Pacific, and what scientists track there is the sea surface temperature anomaly, how much warmer the water is compared to the long-term average. A moderate El Niño is typically defined by a peak anomaly between about 1 and 1.5 degrees Celsius above average. A strong El Niño ranges from 1.5 to 2 degrees, and then there is a category that is not formally codified in the same way, but is widely recognized in the scientific community, events that exceed 2 degrees Celsius in that region. Those are what we call Super El Niños, and they are rare. In the modern instrumental record, which spans several decades of high-quality satellite and buoy data, only 2 events clearly cross that threshold in a sustained way: the 1997 to 1998 El Niño and the 2015 to 2016 El Niño. These are not just statistical outliers. They are events that fundamentally reorganize the atmosphere on a global scale. The 1997 to 1998 event peaked at roughly a 2.4 degrees Celsius anomaly in the Niño 3.4 region. The 2015 to 2016 event reached around 2.6 degrees Celsius. Those numbers may not sound dramatically different from a 1.5 degrees Celsius or 1.8 degrees Celsius anomaly on paper, but in a nonlinear system like the coupled ocean-atmosphere system, that difference matters enormously. The impacts of those events were not just stronger versions of what happens during a moderate El Niño, they were qualitatively different. What that means in practice is that the atmospheric circulation patterns they produced, the jet stream configurations, the storm tracks, the distribution of rainfall and drought, did not simply intensify existing patterns, they shifted them. The teleconnections, which is the term used to describe how changes in one part of the climate system influence distant regions, became stronger, more widespread, and more persistent. Entire regions experienced sustained anomalies that lasted for months, sometimes seasons, rather than short-lived events. That is the category we are talking about when we discuss the possibility of a Super El Niño developing in the current cycle. And it is important to be very clear here. This is not a confirmed outcome. It is not even the most likely outcome based on current data. But it is no longer a fringe scenario either. The latest probability assessments coming from forecasting institutions like the Climate Prediction Center have been trending in a direction that deserves attention. The likelihood of El Niño development in the coming months has been increasing with successive updates, reflecting the same signals we have been discussing throughout this analysis. The rapid warming of the ONI, the presence of significant subsurface heat anomalies, and the continued eastward propagation of that heat via Kelvin waves. More importantly, when you look inside the ensemble forecasts, the collections of multiple model runs that explore different possible evolutions of the system, you start to see something that was not as prominent just a few months ago. A subset of those model runs is producing peak Niño 3.4 anomalies that exceed the 2-degree threshold. Not all of them. In fact, many still fall below that level. But the presence of those high-end outcomes in the ensemble spread is significant. In forecasting, the distribution of possible outcomes matters as much as the average. If all the models cluster tightly around a moderate outcome, confidence is high. But when the spread widens, and especially when the upper tail of that spread begins to extend into extreme territory, it tells you that the system has the potential to evolve in ways that are more intense than the average projection suggests. A few months ago, a Super El Niño scenario for this year would have been considered a low probability edge case. Today, it sits within the envelope of plausible outcomes that scientists are actively evaluating. That shift in status, from unlikely to plausible, is what makes this moment different. It does not mean that a Super El Niño will happen, but it does mean that the conditions necessary for one are present enough that it cannot be dismissed. If we take that possibility seriously, the next question becomes, what would it mean specifically for regions like North America? Because the impacts of a Super El Niño are not evenly distributed. They manifest differently depending on geography, season, and the interaction with other atmospheric patterns. Looking back at the 1997 to 1998 event provides one of the clearest reference points. During that winter, the jet stream across the United States shifted significantly southward. This altered storm tracks in a way that brought an unusually active parade of storms into California and the southern tier of the country. The result was a combination of heavy rainfall, flooding, mudslides, and widespread infrastructure damage in regions that were repeatedly hit by storm systems. At the same time, the northern tier of the United States experienced a very different reality. With the storm track displaced to the south, those regions were left warmer and drier than average. This is a key feature of strong El Niño events. They do not simply increase precipitation everywhere, they redistribute it. Some regions receive far more than normal, while others receive far less, sometimes simultaneously. Temperature patterns are also affected in ways that align with what we are already beginning to see. Strong El Niño events are associated with above-average winter and early spring temperatures across much of the central and eastern United States. That means the kind of premature warmth we're seeing in April 2026, temperatures that feel more like early summer, can become a sustained pattern rather than a brief anomaly. Instead of a few days of record heat, you can see entire seasons trending warmer than normal. Then there is the question of tropical cyclones, which introduces another layer of complexity. One of the most commonly cited effects of El Niño is its tendency to suppress hurricane activity in the Atlantic. This happens because El Niño increases vertical wind shear over the tropical Atlantic, disrupting the development and intensification of storms. It is often presented as a kind of trade-off: warmer Pacific, fewer Atlantic hurricanes. But that framing is incomplete. The suppressive effect on the Atlantic depends on the strength and structure of the El Niño, and it does not apply uniformly across all ocean basins. At the same time that El Niño is increasing wind shear in the Atlantic, it is creating highly favourable conditions for cyclone development in the eastern and central Pacific. Warmer water, lower wind shear, and increased atmospheric instability combine to enhance storm activity in those regions. In the case of a super El Niño, this redistribution can become more pronounced. The Atlantic may indeed see reduced activity, but the Pacific can become significantly more active. The global number of storms may not decrease in a meaningful way. Instead, the location and intensity of those storms shift, creating very different regional risks. This is where recent events start to feel less like isolated anomalies and more like early signals. The rapid intensification of Super Typhoon Sinlaku into a Category 5 storm in April, well before the traditional peak of the season, occurred over ocean waters that were already warmer than typical for that time of year. That kind of early season intensity is not what you expect in a neutral system. It suggests that the ocean has already reached a state capable of supporting extreme outcomes. If that state persists and evolves into a fully coupled El Niño system, the Pacific basins could see a continuation of that pattern. Storms forming earlier, intensifying more rapidly, and potentially reaching higher peak intensities. Again, this is not a certainty. But it is consistent with the physical conditions we are observing. When you step back and look at all of these pieces together, a clearer picture begins to form. The possibility of a super El Niño is not just about one number crossing a threshold. It is about the combination of factors that would allow that threshold to be reached and the broader system response that would follow. It is about a Pacific Ocean that is already warm at the surface, significantly warmer below the surface, and embedded within a global ocean that has just set an all-time temperature record. That combination has not been observed in exactly this form before. The 1997 to 1998 and 2015 to 2016 events provide the closest analogues we have, but both occurred on top of lower baseline temperatures. The current system, if it evolves into a super El Niño, would be doing so from a starting point that is already elevated. The honest summary, then, is not one of certainty but of risk framing. A super El Niño scenario is plausible. It exists within the current ensemble spread of forecasts. It is being actively analysed by scientists because the underlying conditions support its possibility. And if it does verify, it represents a level of forcing on the global atmosphere that, based on historical analogues, has the potential to produce some of the most significant weather and climate impacts we have seen in the modern era. That does not mean it will happen, but it does mean that ignoring it, dismissing it as hyper-exaggeration, would be a mistake. The data does not support dismissal. It supports attention. Part 15. The unusual risk nobody talks about. There is a specific scenario that sits right at the intersection of everything we have been building toward, and it almost never shows up in mainstream discussions of climate risk. Not because it is impossible, and not because it lacks a physical basis, but because it exists in that uncomfortable space where probability is low, consequences are high, and historical precedent is limited. It is exactly the kind of scenario that becomes more relevant when the underlying system changes, when baselines rise, when anomalies stack, and when the boundaries of what is normal begin to shift. Right now, along the coasts of California and Baja, California, sea surface temperatures are running at levels classified as a Category 5 marine heatwave. That is the highest category on the scale, representing conditions that are far beyond typical variability. We have already talked about what that means in terms of ecological impact, stress on marine ecosystems, disruptions to fisheries, cascading effects through the food web. But there is another implication that receives far less attention, and it has to do with the physics of tropical cyclones. Tropical cyclones, whether you call them hurricanes or typhoons depending on the basin, are fundamentally heat engines. They draw their energy from warm ocean water. For a storm to form and maintain its intensity, it needs a sufficiently warm surface layer, typically around 26 to 28 degrees Celsius, and it needs that warmth to extend deep enough into the water column that the storm does not immediately cool its own fuel source through mixing. When those conditions are not met, storms weaken. When they are exceeded, storms can intensify, sometimes rapidly. Historically, the waters off Baja, California and the Southern California coast have been too cool, especially outside of late summer and early autumn, to support sustained tropical cyclone activity. Storms that form farther south in the eastern Pacific tend to weaken as they move northward, encountering cooler waters that effectively shut down their convective engines. That has been a reliable boundary condition for decades, but that boundary is not fixed, it is defined by temperature. And temperature, as we're seeing right now, is changing. In April 2026, portions of the northeastern Pacific along Baja, California, are already approaching or exceeding the temperature thresholds typically required to support tropical cyclone maintenance. Not in September, not at the seasonal peak, but in April, months ahead of when those conditions would normally be expected if they appeared at all. That does not mean the entire coastline is uniformly at that level, and it does not mean every necessary condition for storm development is in place. But it does mean that one of the key limiting factors, the availability of sufficiently warm water, is no longer as restrictive as it used to be, and once that constraint begins to loosen, a new category of possibility opens up. To understand what that looks like, it helps to go back to one of the few historical examples that even comes close. In September 1997, during the peak of one of the strongest El Niño events on record, Hurricane Nora formed in the eastern Pacific and followed a highly unusual path. Instead of weakening rapidly as it moved northward, Nora maintained significant intensity along the Baja California coast. It eventually made landfall in Mexico and continued northward, bringing substantial rainfall into parts of the southwestern United States, including Arizona and Southern California. Nora was not just another hurricane, it was an outlier. Its track and persistence were enabled by ocean temperatures that were unusually warm for that region, even in September. The 1997 to 1998 Super El Niño had elevated sea surface temperatures along the Baja coast to levels that allowed the storm to sustain itself farther north than would typically be possible. Even then, it was a rare event. Now, consider the present moment. The waters off Baja, California in April 2026 are, in some locations, already approaching the temperatures that supported Nora's unusual behaviour in September 1997. That is a shift in timing that is difficult to ignore. It suggests that the seasonal window during which such conditions could exist is expanding, potentially by months. That does not mean a Nora-like event is imminent. It does not even mean it is likely. Tropical cyclone formation and evolution depend on a combination of factors, not just sea surface temperature. You also need low vertical wind shear, so that the storm structure is not torn apart by differing wind speeds at different altitudes. You need a pre-existing disturbance, something like a tropical wave, to initiate the process. You need sufficient atmospheric moisture to sustain convection. These ingredients do not align perfectly just because the ocean is warm. But the point of this scenario is not to claim that such an event will happen. The point is to recognize that the range of what is physically possible is expanding. When ocean temperatures reach thresholds that were previously rare or confined to a narrow seasonal window, they remove barriers that used to limit certain types of events. And when those barriers are removed, even temporarily, the system gains new pathways. This is what risk looks like in a changing baseline environment. It is not just about increasing the intensity of familiar events. It is about enabling event types, timings, or combinations that were previously constrained. A storm tracking unusually far north along the Baja coast and impacting the southwestern United States is not a new phenomenon in absolute terms, but the conditions that allowed it to happen in 1997 were tied to a very specific set of circumstances at a very specific time of year. What we are seeing now is a shift in those underlying conditions. That shift moves this kind of event out of the category of rare seasonal anomaly and into the broader category of low probability, high impact scenarios that can exist over a longer portion of the year. And those are exactly the scenarios that tend to be underweighted in both public discussion and sometimes in planning. Not because they are unimportant, but because they are difficult to quantify and lack a dense historical record. There is also a tendency to analyse risks in isolation. Heat waves are discussed as one category, marine heat waves as another, tropical cyclones as a third. But in reality, these are all expressions of the same underlying system. The same ocean heat that is elevating temperatures along the Baja coast is part of the broader Pacific thermal anomaly that is also influencing atmospheric patterns over North America. When you connect those dots, the picture changes. The record April heatwave along the eastern United States, driven by a highly amplified ridge, is not an isolated atmospheric quirk. It is linked to the same large-scale redistribution of heat in the Pacific that is raising sea surface temperatures thousands of miles away along the California coast. The subsurface warming, the eastward propagation of heat, the basin-wide coherence of the anomaly, these are not separate stories. They are different manifestations of the same process. And when that process reaches certain thresholds, it does not just produce one type of extreme event, it expands the envelope of what the system can produce across multiple categories. That is why focusing on any single outcome, just the heatwave, or just the marine anomaly, or just the potential for storms, can be misleading. The real signal is in the combination. The Pacific right now is not just warm. It is structured in a way that allows heat to influence both the ocean surface and the atmosphere in coordinated ways. The Category 5 marine heat wave off Baja is a surface expression. The subsurface anomalies are a deeper reservoir. The atmospheric response over the United States is another layer. Together they represent a system that is both energized and interconnected. When you view it through that lens, the Baja scenario is not an outlier. It is an example. An illustration of how the current configuration creates possibilities that would have been much harder to achieve under previous baseline conditions. It shows how the same underlying driver can manifest in very different ways depending on location, timing, and the interaction with other factors, and it reinforces a broader point that runs through everything we have discussed. The significance of the current moment is not confined to any single metric or event. It lies in the way multiple signals are aligning: elevated global ocean temperatures, significant subsurface heat in the Pacific, early atmospheric responses, and localized extremes that are already pushing into unusual territory. The Baja coast in this case becomes a kind of preview window, a place where the ocean state is revealing capabilities that the system possesses right now, even if they are not fully realized in the atmosphere yet. It is a reminder that the system does not need to produce the most extreme outcome for that outcome to be relevant. The mere fact that the conditions supporting it exist changes the risk landscape. And that brings us back to the central thread. The same Pacific heat that is contributing to record-breaking warmth in April across the eastern United States is also raising coastal water temperatures to levels that can support entirely different kinds of extremes. Different expressions, same source. Once you see that connection clearly, it becomes harder to think of any single event in isolation. Because what we are really watching is not a heat wave, or a marine anomaly, or a hypothetical storm track. We are watching a system whose boundaries are shifting, and with them, the range of what is possible. Part 16. The core mystery. End on tension. Let us come back to the beginning. Let us come back to Washington, D.C. in mid-April, sweating through temperatures that belong in July. Let us come back to Boston, where the air mass overhead has the thermal signature of a summer that arrived months early. Let us come back to the National Weather Service offices that adjusted their forecasts upward and still watched reality blow past them. Let us come back to the fundamental question that started all of this. Why is this happening now? The scientific framework we have built across this video provides a partial answer. Subsurface Pacific warming at 5 degrees Celsius above average is migrating eastward on downwelling Kelvin waves, loading the upper ocean thermal structure from below. Sea surface temperatures are responding, reaching Category 5 marine heat wave intensity off Baja, California, and setting record April highs along the California coast. The ONI, running as a lagging indicator of a rapidly transitioning system, is already on its way to crossing the El Niño threshold, while the atmosphere has been responding to leading indicators that have been signaling transition for months. A record global ocean baseline for any month in instrumental history is elevating the floor on which all of these anomalies operate, and the atmospheric response to all of this combined forcing is an amplified Rossby wave pattern that is producing simultaneous extremes across 5 different categories of weather, with the eastern United States sitting at the top of a heat dome that is ranked at the 99th percentile of the entire historical April record. That is the framework. But the mystery is not fully resolved by the framework, because here is what still does not have a complete answer. The atmosphere appears to be responding more strongly to this forcing than the forcing alone would predict. The models, which encode the best physical understanding of how atmospheric circulation responds to Pacific Ocean temperatures, have consistently underestimated the magnitude of the current pattern. The experienced forecasters who corrected the models in the direction of greater warmth were still outrun by reality. The gap between prediction and observation has not been random. It has been systematically in the direction of stronger than expected atmospheric response. And that systematic gap is the unresolved mystery sitting at the centre of this story. One possibility is that the models are not fully capturing the current magnitude of the Pacific forcing, that the subsurface anomalies, the elevated baseline, and the compound nature of multiple overlapping signals combine to produce a forcing that is genuinely stronger than the model's assumptions about the current state of the Pacific suggest. This is plausible, and it implies that as the subsurface heat continues to surface and the El Niño forcing strengthens, the models will progressively underestimate the atmospheric response until they catch up to the actual thermal state of the ocean. That is an uncomfortable possibility because it means we may systematically underpredict what comes next. Another possibility, which the science does not yet definitively support or refute, is that the atmosphere itself has become more sensitive to ocean forcing, that decades of gradual warming have shifted the background state of the circulation in ways that amplify the response to a given forcing beyond what historical relationships would predict. If the jet stream has systematically weakened, if the Arctic amplification has altered the temperature contrasts that govern wave behavior, if the elevated ocean baseline has changed the distribution of tropical convection in ways that amplify downstream teleconnections, then the same El Niño forcing that produced specific atmospheric responses in 1997 and 2015 might produce larger responses today. This would mean that the historical analogues we rely on to predict the impacts of El Niño events are systematically conservative about what the current climate system will actually produce. We do not know which of these possibilities is correct. We may not know for some time. What we do know is that the system is operating outside the range of normal prediction at a moment when it has not yet reached its peak forcing. The April heat wave is a preview. The Pacific has not finished loading. The subsurface anomaly has not fully surfaced. The El Niño classification has not yet been officially declared. The Walker circulation feedback loop that drives the most extreme El Niño impacts has not yet fully activated, and the atmosphere is already at the 99th percentile of its April historical behavior. There is a narrative that gets told about extreme weather events. The narrative says, this was unusual, but here is why it happened. Here is how we understand it. Here is what the science tells us about it. That narrative is comforting because it implies comprehension. We saw the thing, we explained the thing, we can predict the next thing. That narrative is partially true for the current event. We understand the broad strokes of why April 2026 is doing what it is doing. But there is a residual, the gap between prediction and reality, between expected forcing and actual atmospheric response, that the narrative does not fully account for. And that residual is the part that should stay with you, because it suggests the atmosphere is telling us something we have not yet fully learned to hear. The eastern United States is baking in April heat that belongs in summer. Beneath the Pacific, 5-degree above average water is still moving eastward, still approaching the surface, still waiting to fully arrive. A Category 5 marine heat wave is established along the Baja coast, a super typhoon formed in April with peak season ocean heat content supporting it. The global ocean set a record temperature for any month in history just 1 month ago. El Niño has not officially started. The Walker circulation feedback has not yet activated. The subsurface discharge has not completed. Every tool we have for prediction underestimated this moment, and this is not the moment. This is the approach. The record April heat, the flooding rivers in Michigan, the fire weather in Texas, the out-of-season typhoon in the Western Pacific, the Category 5 marine temperatures off California. These are not separate events that happen to cluster in April 2026. They are dispatches from a planetary system in a state of transition whose endpoint we cannot yet clearly see. They are the kind of signals that, in hindsight, look like they were screaming the answer at anyone who was paying attention. The kind that get quoted in the retrospective analyses written after the main event arrives and people ask, was there any warning? There was. There is. Right now, today, in mid-April 2026, with the eastern United States baking in heat that no model fully predicted and no April in the historical record quite anticipated, the system is not finished building toward whatever it is building toward. The Pacific is not done speaking, and the atmosphere, the same atmosphere that outran every forecast we threw at it, that generated 5 categories of simultaneous extreme weather from a forcing that has not yet fully arrived, that responded to a precursor as though it were the main event, the atmosphere has already started responding. And it has not heard the whole message yet. The ocean is still speaking. The question is whether we are listening carefully enough to understand what it is saying before we find out the hard way